Here's another 2D particle equilibrium problem. So in this case, we have a box that is sitting on a rough surface. It's not moving, right? We're in statics, we're not in dynamics. We know that the slope of this ramp here of this is 17 degrees. And we're now asked to find the normal force, which is going to be perpendicular to my slope, and also the friction force, which has to be parallel. Right, so those are the two things that we're supposed to find, which means we'll draw ourselves a free body diagram. Let's say we choose a point, reduce everything to a point right there, right? So this would be our point. And now we have the friction force. We said the friction force is parallel to our slope. And of course, the box wants to move downward, so our friction force has to be directed opposite to that. Right? That's all learned in physics. Right? So that would be the friction force. We know our normal force is going to be perpendicular to the surface, pointing upward. So this would be our normal force. And of course, the last one we have is the weight of this mass here, and that's going to go straight downward. So that's going to be something like this, where this is going to be the weight. Now we could set our coordinate system as x and y. But in this case, because we already have two that are kind of not in the x and y direction but are perpendicular together, we can just use that as our reference frame, right? So we can do a coordinate system that looks like this. In this case, I like to call this the parallel direction and the perpendicular direction. So that means we now have to have our weight be resolved in those two directions, right? So we know there's a component that is, no, let's do this blue. That looks a little different. Have all those colors. All right, so we have a component that's going to be in the perpendicular direction and a component in the parallel direction. All right, so we can call this W perpendicular and this W parallel. And of course, lastly, we know if this angle is 17, then that angle is 17 degrees as well. With that, I think we have all the information that we need to solve our problem. So what are we going to do? We're going to write our two equilibrium equations. Now instead of in x and y, we'll write them in parallel and in perpendicular. All right, so we can write sum of forces in the parallel direction have to be equal to 0. N is equal to what? What do we have in the parallel direction? Well, we have F. F is pointing in the positive direction of our coordinate system here, so it'll be positive. F, and then our W parallel is going to be is pointing opposite of that, so it'll be minus W parallel. Well, what is W parallel? That's just going to be W times, this is the opposite leg, so W times sine of 17 degrees. So that means that if we solve this for F, F is going to be W times sine of 17 degrees. W, well, we're given the mass, so that would be M times G times sine of 17 degrees. So that would be, the mass was 270 kilograms times 9.8 meter per second squared times sine 17 degrees. That means our F is going to be 774 newtons. So that would be the friction force, right? Basically the force that's helping hold the block from sliding down. All right, so that was one unknown. Other unknown we'll get if we go in the perpendicular direction. F perpendicular equal to 0. Very important to always note that. What do we have in the perpendicular direction? Well, we have the normal force going positive, so upwards, so positive, and then W perpendicular going downwards, so negative. So that means N minus W times, now this is this part which is the adjacent leg, so cosine of 17 degrees, which means the normal force is equal to W times cosine 17 is equal to M times G times cosine 17 degrees is 270 kilograms times 9.181 meters per second squared times cosine of 17 degrees. And I can plug that into a calculator and I get 2,530 Newton for my normal force. Now this makes sense to me, right? Most of the support for this block comes from it sitting on the support, not from being resistant from sliding, right? So 10 times the mass here would be 2,700 Newton. So we can see, because of this very small angle, most of the weight is being supported by the normal force and just a little bit by the friction force. So this was the way to get the normal force and the friction force for a block that is sitting on a rough slope.